General relativity, step by step. We've been fooling around with the Einstein field equations, and we've brought them into this form here, in which everything is known. Well, everything's got a reasonable interpretation at least, except for this value of k here, which is still eluding being pinned down. So I'm going to pin it down and have done with it. And then we can start talking about what the Einstein field equations mean. So what we do is we need the weak field limit, which I've spent quite a long time fooling around with, and basically I'm going to remind you that the 0, 0 component of the metric tensor was minus 1 minus 2 phi over c squared. Okay, well that's one thing that we need in the weak field limit. So we're going to try and require this and see what that. Oh, and phi was the Newtonian potential, was minus gm over r in the Newtonian case. It's just the gravitational potential in the weak field limit. Okay, so what else have we got? Well, we need the tidal equation, d2ni by dt squared equals, see if I can get this right, di2 phi, it's the same thing, by di x I di x j nj. And that was the tidal field equation. Tidal, write that out again, tidal field equation. We've also got the relativistic equivalent, d2n by d tau squared, component alpha, equals minus the Riemann-Christoffel tensor, alpha, of course the alphas match, times mu nu sigma, u sigma, see if I can get this right, u mu, nobody can remember all this, you just need to write it down, and all I'm doing is copying it from my notes. Yeah, that looks about right. Now we might be able to start to bring this equation to bear on the weak field limit. You'll remember that the weak field limit, everything has got slow velocities, the gravitational field is stationary. What else? Weak as well. Oh yes, of course, the phi over c squared has got to be very, very small. And we saw that it was quite small even for white dwarfs and stuff like that. We'll relax that assumption later on, of course, when we start thinking about black holes. But for the moment, we're just going to keep that. We're going to keep that weak field assumption in place. Okay, so what have we got? What happens with this equation here? No, not that equation. This equation. What happens to this equation in the weak field limit? Well, we can just replace it with the space-like components, d tau squared. You'll remember that I is 1, 2 and 3, and we'll use Greek letters like mu and nu and pi and stuff, and sigma, to mean 0, 1, 2, 3. And what does that equal? That equals minus r. And then we can put an I there, mu nu sigma, u mu, n nu, u, what's left? Sigma on the right hand side. And now we start to invoke the weak field approximations. Now we'll remind ourselves that because these are 4 velocities, the only component that's interesting, or the only component that's non-negligible, is the 0 component. So that basically forces us to consider only, we're summing over mu and sigma, but they're all very small components. So mu equals sigma equals 0. That's all we're interested in. So it equals minus ri 0 nu sigma equals 0 u 0 n nu. We'll come back to nu and think about that in a minute. U 0. That's right. Yes, that's correct. So these guys here are just 1. So it's minus ri 0 nu 0 n nu. equals minus Ri 0, 0, 0, n 0 plus Ri 0. Let me just write it out. 0 n j. Whew. Okay. And this term, I can't remember exactly which screencast it was, but that by symmetry, we know that this term is equal to 0. It was one of the screencasts I did on the Riemann-Christoffel tensor. It's Riemann tensor revisited, but I forget the exact number of it. So that equals minus R I O J O, sorry, 0J 0 N J. And what was the left-hand side? It's up here. It's this thing here. It's D2N I by D. Can I replace it with a T? Yes, it's a weak field limit. So I can put dt squared or d tau squared there. It doesn't matter. Yeah, that's right. So this I here, I'm going to rewrite that in red. Just a minute. I'm going to rewrite it in that red, just to remind myself that this index here is the free index, and we're summing over j. And because of the weak field limit, I can consider this index and this index just to have the value 0, because everything else just vanishes. So that's quite a nice thing. I'm going to stop there, and I'll develop this in the next screencast. Stop.